Doug Jenkins has worked on the design of bridges and related structures since graduation from the University of London in 1972. In 1993, he joined the Reinforced Earth Company as engineering manager, where he was responsible for the design and development of their TechSpan buried arch structures. Doug was head of the International Committee, responsible for TechSpan development, and in this role managed the development of software, design procedures, and training material. Since 2000, he has worked as an independent consultant, providing analysis and design services for bridges and buried arch structures.
So first of all, looking at the limit states defined in most of the international codes. Typically the codes define two limit states, a serviceability limit state, which looks at whether a structure will need unscheduled maintenance or repair, or will it perform less well than intended, and an ultimate limit state, which in most cases is defined as a collapse condition. But when we look at the particular requirements in the code, we find that they are almost all looking at strength of individual sections and avoiding damage. So in my opinion, we need a third limit state, which is looking at the total collapse of a structure. Will it fall over? And that should be differentiated from the ultimate limit state, which is we could call a strength limit state, looking at the strength of a particular section. So if we look at the reason for this, if this is an earthquake that occurred in Iraq a number of years ago, and we can see all those structures in this picture have all reached their strength limit state. They're all quite severely damaged, but obviously anybody living in those structures which are still standing will be very much better off than those who were unfortunate enough to be in the structures which have totally collapsed. But it's not just earthquakes we need to look at. This is a structure in Sydney, which was over the Lane Cove Tunnel during construction, and there was a collapse of the tunnel underneath, which caused a partial collapse of the foundations of the structure, and obviously caused a lot of damage to the structure. But nobody was hurt in this. The bulk of the structure, other than the one corner, stood up. So all the living accommodation survived that event without collapse and without injury to anybody, any of the occupants. Another example is this impact of a excavator on a low loader with a bridge structure. Again, obviously this structure is exceeded its ultimate limit state, but it hasn't collapsed, and in fact the driver of the truck walked away from this event totally unhurt. Whereas a structure which had perhaps was not so well designed, if it had caused total collapse, the driver probably would have been killed, and any vehicles passing over the top would also be in great danger. Another example of a structure which did not behave so well. This was from a couple of years ago in the USA, a wooden balcony with a party in a rented accommodation, and there were about 20 people on top of that balcony at the time it collapsed, and most of them were killed in that incident, and all the rest were very badly hurt. We might think that that sort of damage is more likely to occur with a wooden balcony, and perhaps concrete structures are not so susceptible to that sort of damage. Well, maybe they are, and maybe they aren't. This is some shots of some concrete balconies on the Gold Coast in Australia. And again, the strength of those balconies to resist their design loading must be open to question. Another example of a structure which had the potential for very severe consequences of possible failure is the Citicorp building in the USA. This was an unusual structure which, for reasons of avoiding surrounding structures, was built with the main columns positioned along the midpoint of each side rather than at the corners. So that was an innovative design. It was completed in 1977, and during the course of construction, the contractor suggested replacing the critical welded joints with bolted connections for a small saving in the cost. After the completion of construction, a student contacted the chief structural engineer and queried the design for wind loads. So the student had done a calculation and thought that the structure was not capable of sustaining the design loads, particularly when they were coming at an angle rather than face on to the structure. The student was actually fobbed off, but the engineer actually reviewed the design and found it to be inadequate, and found that it was likely to fail under winds with a return period of 16 years. And that collapse could result in up to 200,000 deaths, which is perhaps an exaggeration, but even so, it quite clearly a total collapse of that structure would result in a large number of deaths. So it was decided that the structure should be redesigned, and it was actually retrofitted and designed for a wind load with a 200-year return period. It was actually retrofitted in secret, so the work was done overnight, and it wasn't known to the public until 25 years later, when the design engineer actually revealed what had happened. And this is his recollection of the event that led to the redesign. He said he was very nice to the young man, the student who called him, but he said, "Listen, I want to tell your teacher that he doesn't know what the hell he's talking about, because he doesn't know the problem that had to be solved." And he promised to call back after the meeting and explain the whole thing. In fact, he never called the student back, but he did review the design. But an interesting factor of the case is this is actually a photograph of the student, and she hasn't had a sex change. She's always been a woman. So whether the engineer just misrecalled the events, or whether he never actually spoke to her, is not actually clear. But for the lessons that we learned from this event, I think there's actually a few things that we can learn for this. One is the question is why should they accept an alternative connection detail for these critical connections, which resulted in a reduced strength for such a small cost saving. And the other important question, I think, is that in the final revised design, it was designed for wind speed with a return period of 200 years. And the question is that adequate given the consequences of failure of that building? And if it's not, what should it be? And all these things are things which are still open questions in pretty well all design codes around the world. So let's just look at an example in a context of concrete design, looking at the statistical analysis of possible concrete strengths not being up to the required level. So looking at an example of very high strength concrete and looking at the actual statistical results from an actual structure, the mean strength of the concrete was 95 MPa. The design strength was 80 MPa, and the standard deviation was 6.1 MPa. Now, if we assume a normal distribution, and we look at what is the probability of the event of that concrete being as low as 32 MPa, our normal statistical distribution would say that event would happen one time in 2.6 times 10 to the minus 25. And what that means in terms of return period is several thousand times the length of the life of the universe. So as close to zero as you can get. Before we look at that in a bit more detail, I'd like to mention a book which has really changed the way I look at how we approach these questions. This book was actually looking at financial events. It was published in 2007, and it predicted the global financial collapse immediately before it actually happened. Now, this book, it was actually written by an academic who uses the word academic as a term of abuse, so he tends to dismiss theoretical analysis totally. In many ways, what he says is oversimplistic. So I like to compare it to the streets of Naples, which have way too much rubbish, but they also have many things which are well worth looking at. So in the case of the book, The Black Swan, we should not dismiss the whole book because in some ways it's oversimplistic. I think this quote from the Black Swan is really worth remembering. So So let's revisit the cylinder results and include the black swans, the unexpected events. So we all know, I think, that although typically concrete has a small standard deviation, there are events that happen which mean that it may have much lower strength. So this we've looking at our statistical distribution here, and we've added in the black swans. Now, if this had been the actual record of deliveries to this particular building, that would have obviously shown up in the events. But suppose the actual number of the black swans was much lower. So it's a sufficiently low level that it doesn't show up in the recorded cylinder strength data. But even with that low level of events, when we of unexpected low strengths, when we look at a large number of records over the course of construction of a large building, we'll find that the chance of getting a very low strength with the numbers I've chosen has risen to 5%. So quite a significant chance. And even if I've overestimated the number of black swans quite significantly, the chance of a very low batch could still be significant, and is still high enough that we should consider it that possibility in the design. So now let's have a look at how these things are handled in a typical codes practice. So in the international codes, including the Australian codes, there's an ultimate limit state defined, which is characterised as a requirement to avoid structural collapse. But almost all the detailed provisions deal with the strength of a single cross-section or a single member. They do cover earthquake and impact load provisions in some cases, particularly where the earthquake levels are high, such as in New Zealand and Japan. So there are provisions to allow for significant damage to the structure, providing there is no collapse. But those requirements are typically presented as being the same limit state as those limiting design loads to less than the section capacity. So if we look at some specific examples, in the Eurocode number 8, which deals with earthquake loading, looking at retrofitting for existing structures, it refers to a near collapse limit state. But Part 1 treats checks for strength and collapse as being the same ultimate limit state. Eurocode 2 has specific provisions regarding disproportionate collapse. And in the UK, there's an improved document A giving further detailed provisions. But those historically relate to the collapse of the Ronan Point structure in the UK in the early 1970s. So they have a long history of codes dealing with avoiding disproportionate collapse. In the Australian and New Zealand codes, the codes do talk in general terms about requiring robust behaviour and requiring alternate load paths, but they have no specific guidance. Also, the AS 3600, the concrete building code, requires robust behaviour but gives no specific guidance. The commentary requires that removal of any one member should not cause progressive collapse, but that's hidden in the commentary and is often overlooked. The American State Highway Organization code for bridge design is a bit different. It actually recognises the extreme event limit state, which is to ensure that structural survival of a bridge during a major earthquake or flood, or under collision of a vessel or a vehicle. And it says in the commentary that the extreme event limit states are considered to be unique occurrences whose return period may be significantly greater than the design life of the bridge. So they do recognise an extreme event limit state as being something different to the standard ultimate limit state. Looking at risk management, this has been something that's been talked about for some time. Looking at a paper written by Beebe in 1999, he talked about requiring 3 independent requirements: adequate safety factors, adequate control of the design and construction process, and adequate robustness. So he noted that statistical analyses used to calibrate code, load and resistance factors do not include significant sources of risk. Also, that increasing the design loads or reducing the design strength capacity may have little effect on the risk of collapse. So looking at how these things are handled in the legal requirements, there are legal requirements outside the design code provisions. So in Australia we now have a federal safety and design legislation that requires all risks to be eliminated or minimised so far as is reasonably practicable, often shortened to SFRAP. In the design codes, they typically require risks to be made as low as reasonably practicable. So they focus on the risks. There's a question about whether these phrases mean the same thing. Does a hazard-focused approach lead to different outcomes to a precaution-focused approach? There was a paper written by Richard Robertson. It was published in the Engineers Australia magazine. This was from a couple of years ago, which was saying that the codes focused on reducing estimated risk to an acceptable level were not consistent with the legal requirements. And this was discussed in an earthquake engineering newsletter from 2014, an article by Paul Somerville. He quoted Chief Justice Gibbs of the High Court of Australia, who made the point that where it is possible to guard against a foreseeable risk, which though perhaps not great, nevertheless cannot be called remote or fanciful, by adopting a means which involves little difficulty or expense, the failure to adopt such means will in general be negligent. And the point is that it's still negligent even if that was not a requirement of a design code. He also quotes a comment by another earthquake engineer who said, what I'm contemplating is a change in mindset on the part of structural engineers. We seem to be too driven and limited by standards and codes, and I'm not denying their usefulness, so that a deep understanding of structural behaviour is not seen as vital. So, to satisfy these legal requirements, design code provisions should be consistent in their approach to risk reduction and in terminology. They should also consider what is meant by reasonably practicable. It may seem obvious what that means, but when you look at particular cases, it's perhaps not so obvious. Where there are different levels of precaution are required for different classes of structure, these differences should be explicitly stated. And codes should also review the legal requirements and consider what else needs to be changed in the codes to ensure that they satisfy all the requirements of the law. So in summary, the design codes combine design states requiring radically different approaches to analysis and design under the same limit state, the same ultimate limit state. Design provisions for prevention of collapse are well developed for some events and in some codes, for instance earthquakes in high seismic regions and impact, but there is little or no requirement to consider other causes of collapse, for instance corrosion effects or grossly substandard materials or loss of foundation support. So following on from that, I would recommend that codes should actually look at 3 separate levels of limit state. There should be a serviceability limit state, which we have, and that really doesn't need changing. Then what we currently call the ultimate limit state, we're really looking at strength, so we still need to look at and ensure that no individual cross-section or member should fail or suffer excessive deformation under very high loads. But then we should also look at more extreme conditions, look at the levels of loading at which a structure is on the point of substantial or total collapse, and ensure that doesn't happen even if the risk is very low. So correct consideration of the collapse limit state should not be limited to seismic and impact loading, but should also include all potential causes of collapse, including loss of support, deterioration of material properties, improper construction procedures, the effects of fire, and also extreme loads due to any cause, but also in things like parking structures. And we should also consider where the degree of collapse is related to the classification of the structure and the consequences of failure. There should be specific guidance regarding the type of analysis and the level of robustness required. And this particularly applies to things like parking structures, which are typically designed to lower standards than structures which are occupied all the time. And we really should consider whether that's appropriate or not. So we should review and revise code intent and provisions and wording to ensure compatibility with legal requirements so far as is reasonably practicable. So in summary, to repeat the summary of the recommendations from the Black Swan, the idea is not to correct mistakes and eliminate randomness. The idea is simply to let human mistakes and miscalculations remain confined and to prevent their spreading through the system. And this principle applies also to low probability events with severe consequences. The aim is not to prevent all damage, but to avoid total collapse wherever it's reasonably possible to do that.